So here's another example. So again, there's nothing like this in the tables. It's far more complicated than anything we see in the tables. So we need to write this as a sum of simple terms. That's the first thing to say. So the first thing to do is factorize. Now s squared plus does not factorize, and so you've got a rule 1 and a rule 3, and you cannot factorize. You cannot use the cover up method because it isn't all rule 1s. Okay, so what we're going to do is we'll write down, we've got two, what have we got? We've got two factors, so there's going to be two terms. So we're going to have 107 plus 45s plus s squared divided by s plus 2 times s squared plus 25 equal to, so the rule 1 is a constant over s plus 2, and the rule 3 is a constant times s plus a constant over s squared plus 25. So there, rule 1 and rule 3, you can go back and look at where they're coming from. So constant here, constant times s plus a constant here. So what we're going to do is we're going to write this as a single fraction again with the same denominator. So I might just so we write as a fraction again, but with the same denominator, same bottom. And how we could do that is we can, well, we want s plus 2 times s squared plus 25. So looking at a over s plus 2, we need to multiply that above and below by s squared plus 25. Okay, and that red thing is equal to 1. That doesn't change anything. That should be 25. Okay, plus the second thing we need to multiply above and below by s plus 2. So now that we've got a common denominator, we can write this as a single fraction. So we're looking at a times s squared plus 25 plus bs plus c times s plus 2, all divided by s plus 2 times s squared plus 25. And now we're comparing, so we want the thing in the left-hand corner to be equal to the partial fraction expansion. Partial fraction expansion is equal to the thing down the bottom, so we want the thing in the top left to equal the thing in the top right. Now what's good is the bottoms are the same, and if we want them to be equal for all relevant values of s, we need the tops to be the same as well. So if we force the tops to be each other, this is what we end up with. So we're going to put in clever values of s into both sides and hopefully generate equations to find out everything. Okay, so the question is, we're picking these values of s to put in, and why are we picking these particular values? So the first one is minus 2. Well, minus 2 is chosen because it'll make this equal to 0. Okay, so if I put in s equal to minus 2 into both sides, I get 107 plus 45 by minus 2 plus minus 2 squared is equal to, and where's my calculator? There, a times s squared is, and we need the brackets there, because if you put in minus 2 squared plus 25, as I just said it, you'll end up with 21. Of course, minus 2 squared is plus 4, so you end up with 29, so that's why we have the brackets there. Plus 25, and now we've something that's times 0, because when you substitute in s equal to minus 2 into s plus 2, you get 0, so that's just plus 0. So if we tidy this up, maybe on the next line, we get on the right hand side, minus 2 squared plus 25 is 29. A is equal to, and we'll bang this other bit into the calculator, 107 minus 90 plus 4, 21. So we get this weird 21 over 29. I just want to check, is that okay? Yeah, weird numbers, but there we go. So divide both sides by 29, 21 divided by 29. Okay, so now we're going to, now we haven't got great space here, so I'm going to, hopefully you can do something similar to this. Now we're going to substitute in s equal to 0. Now the thing is, we can't kill anything else. You can't kill s squared plus 25 because that has no real roots. So s equal to 0 is the cleverest thing to put in. You get, say, 107 plus 45 times 0 is 0, plus 0 squared is 0. So I'll just put in plus 0, equal to a, which is 21 over 29. 0 squared plus 25, which is 0 plus 25. Plus b times 0 is just 0. So we'll write it in there. 0 plus c times 0 plus 2, say. And this is good because this is an equation in c alone. So working on the right hand side, I have the 0 plus c is c, 0 plus 2 is 2. So I got 2c. That other thing, 25 by 21 over 29, I'm going to bang into the calculator. It's 525 over 29. Add numbers really, equal to 107. And what do I have to do? And I'm going to do it in one go here because I don't really have the space. I need to take away the 525 over 29 away from both sides. And I need to divide both sides by 2. And if I do that, I get c is 1289 over 29. Weird numbers, but there you go, 1289 over. Ooh. I'm going to have to pause this and figure it out. No, it's actually good. I should have trusted myself. It's nasty, but it's good. Yeah. So what are we going to do next? Well, we're just going to put in the next easiest value, which is s equal to 1. So if I substitute in s equal to 1, I have to pause it right down where I am. I'm going to be plugging in s equal to 1 into both sides of this. But we know that a is 21 over 29. And we know that c is 1289 over 29. There's no harm seeing this. I mean, there's nothing to say that numbers should be nice. So let's see what we get. So I have 107 plus 45 times s. Now if s is 1, it's just 45 times 1 is 45. Plus s squared, which should be 1 squared is 1. Equal to a, which is 21 over 29. Times s squared plus 25, that would be 1 squared, which is 1 plus 25. Plus bs, so that's b times 1. Plus c, which is 1289 over 29. Times, and this suggests that maybe minus 1 might have been a clever value to put in because the minus 1 would have made the next term equal to 1, but actually it's making it 3. 1, s equal to 1 plus 2. So I'm going to do some calculator stuff. Say 107 plus 45 plus 1 is 153. And the next term, 21 over 29 times 26 is giving me 546 over 29 plus. I should probably just multiply this thing out. So I'll get the thing on the right is 1 plus 2 is 3 by b is 3b. And the other thing, 1289 by 3 divided by 29 gives us, these numbers are nasty, 3867 divided by 29. So I'm going to, both of those fractions, I'll take those away from both sides. So I'm talking about 153, or rather 3b is equal to 153 minus 546 over 29, and also minus 3867 over 29. Which is giving me minus 6 over 29. Oh God, I'm gonna have to pause it again. Okay, we're back. I made some kind of a calculator mistake. My apologies. This should be 24. And then we divide both sides by 3. B is equal to 8 over 29. Okay. So now what we want to do is, remember, look at what we're looking at. We want to find the inverse Laplace transform of this thing, which I'm calling big F of s. So it's equal to a over s plus bs plus c over this. And if you put in the values of a, b, c that we found, it's nasty. But it's this. Okay. Now, how are we going to deal with this? The first term is okay. It's basically in the tables. Like the fraction is no issue. Like the 21 over 29 divided by s plus 2 Yeah, so this is just, I mean, you can just, I keep saying this, you can fix that constant there. So that first term is no issue. Now the other one is a little bit messier, this yoke. So it kind of looks like you got an s going on. So it looks like s over s squared plus omega squared. And in fact, we can maybe at this point already say that the 25 is 5 squared, which would go back to cos 5t. So it looks a little bit like cos 5t. It also looks a little bit like, let's be 5. It looks a bit like a sine. So the question is, have we any ideas? And basically what the crack is that you have to just do some manipulations. I think we've seen this before once or twice, but what you have to do here, now I could kind of show this with a plus b over c, and I could say, oh, if you've got this situation, it's a divided by c plus b divided by c, but you might be a bit confused because the denominator we have is s squared plus 25. So I'll just say there's nothing special. I mean, like c is a number, so is s squared plus 25. So that really does cover what we're going to do. But if you're any bit scared, I can do it like this. So you've got a plus b divided by a number. So that's equal to a divided by that number plus b divided by that number. And that's the way it works. Like a kind of silly example of this would be, say, 2 plus 3, say 8 plus 5. So that's 5/13 is 2/13 plus 3/13. So it's just little nicky-nacky algebra things. But anyway, we can split up this term in that fashion. And what you get is you get 8 over 29 times s divided by s squared plus 25, which is 5 squared. So that's the first bit, plus 1289 over 29 divided by s squared plus 5 squared. And now you're in a bit of trouble yet. The first term is easy though, because that's just 8 over 29 times s divided by s squared plus 5 squared. Let's just write that slightly differently. 8 over 29 times s squared plus 5 squared. So that's no issue. The second one's a bit more troublesome, because look at this. This is what we want to get. We're not quite there. But what you can do is the following. You can take out the constant, the 1289. I'm going to write it a bit funny. I'm going to write it as 1289 divided by 29. I'm going to write it like that. So you can take that out, divided by s squared plus 5 squared. And if you put kind of a 1 here, I'm going to be getting rid of this in a second, but that's the same thing. Okay. Now, if you look at the thing that's highlighted with the highlighter, you need a 5 on top. Now, you can't just chuck a 5 there. That's exceedingly dodgy. But that's what you want to do. But if you put a 5 there and put a 5 here, what you've actually done is the original thing you've multiplied by 5 and divided by 5. So it actually makes no difference. So actually, this will work fine. So this is 8 over 29 times a cos. And then the 1289 divided by 29 and also divided by 5 is 1289 divided by 145 times 5 over s squared plus 5 squared. So what we're actually sending back, so the first term was easy, and then fixing the 8 over 29, what am I talking about there? Fix the 8 over 29. Then you're talking about the s over s squared plus 5 squared, send that back, and then fix this. So it works out pretty easy. I don't know, is this done on the next page or what? No, it's done here. So let's send these back using the tables. So this goes back to 21 over 29. 1 over s plus 2 gets sent back to e to the minus 2t. Fix the 8 over 29. And then the s over s squared plus 5 squared gets sent back to cos 5t. That's using these formulas here from the tables. plus 1289 divided by 45. That last term is a sine. And that wouldn't be a damped oscillator. That would be an oscillator with an external exponentially decaying force. Okay, we'll keep on going. Right, so this one, now the bracket I don't really need. So now it's the same crack. We've got a sum divided by something. So you can just do, that's s divided by s to the 4 plus 1 divided by s to the 4. Like if I write, look at the, okay, just 1 minute here. Look at what I just wrote. You have a common denominator, s to the 4, so you can go from right to left. We're just going for, now equals is symmetric, so you can go from left to right as well. So hopefully it's something you can figure out. And then, now here's the thing, if you look at, you need a little bit of manipulation here. Now maybe the easiest thing to say is, I don't want the s on top. Like look at the formula that is in the tables. You can deal with 1 over s to the something. So there's various different ways of dealing with this. Some of you, it might be quite easy. Some of you might go through, I think there's two reasonable possibilities here. We'll look at both of them. So the way that might be familiar to ye, and then the way that may be slightly different. So you could say the first thing is, you could think of it like this. It's s to the 1 divided by s to the 4. And you might remember that division of like powers means subtraction. So that's s to the power of 1 minus 4 plus 1 over s to the 4. And then you've s to the minus 3 plus 1 over s to the 4. And then you remember that negative powers mean division. So it's 1 over s cubed plus 1 over s to the 4, which both can be sent back using the formula below. Now, how I'd probably do it, I can say it just you divide above and below by s, but how would I, if I want to actually write that? So I could say, alternatively, I don't want that s on top, so I divide the top by s, and I divide the bottom by s, and now that red thing is equal to 1, and it makes it look different, but it doesn't change it. So the s by 1 over s gives you the 1, now divided by s, and then s to the 4 divided by s is s cubed. And then they're both things that we can send back. So big F of s gets sent back to little f of t. So the 1 over s cubed, using this formula, go back to t to the power of, not 3, but 3 minus 1, over 3 minus 1 factorial, plus the 1 over s to the 4 gets sent back to t to the power of 4 minus 1, divided by 4 minus 1 factorial, and then we can just tidy up. So 3 minus 1 is squared, 3 minus 1 is 2, 2 factorial is 2, 4 minus 1 is 3, and then 4 minus 1 is 3, 3 factorial is 3 by 2 by 1, 3 by 2 is 6 by 1 is still 6. Okay, so that's that one. And now we're going to enter the world of pain. Okay, so if you're kind of with us up to now, here's where it gets more challenging, or if you're lost, this is where you'll get really lost. Okay, so you've got this thing, and you look at it and you say, okay, it's not in the table, so really what I should be trying to do is write this as a sum of simple terms. I should be doing the partial fraction expansion. So the first thing you do is you try and factorize the bottom. So using the AC method, you multiply a by c, which is 1 by 13 is 13, but 13 is a prime number, so its only factors are itself and 13, and you can't make up 6 with that. Now it's possible that you can still factorize it. So the thing is that the factorization did not work. So the other way, how could you factorize, and if you're doing assignment, whatever, what's it called, assignment 2, this will be relevant. We had the factor theorem that said every root give you a factor. So if you find the roots, you find the factors. So instead, solve equal to 0. This equal to 0. Okay. So if we do this, we use the minus b formula because we can't factorize. And let's see what happens. You get s is equal to minus b, which is minus 6, plus or minus square root of b squared, which is 6 squared, minus 4ac is 13, over 2, and we get minus 6 plus or minus square root. Let's see what's inside that square root. 36 minus 4 by 13. Oh, this. So the roots are complex numbers. So this means no real roots. And that means that there's no real factors. So this cannot be factorized, s squared plus 6s plus 13, without using complex numbers. So we don't go on factorizing using complex numbers. What we're going to do, we're going to go a different route. Okay, now what we might say is maybe the s squared plus 6s plus 13, like of anything in the tables, it looks most like s squared plus omega squared. But maybe could we say that our big F of s here, this 6s plus 1, sorry, where am I going with 6s? 2s plus 1 over s squared plus 6s plus 13. Maybe does this look like a shifted sign? So what's a shifted sign, or shifted cosine first? So cosine is s over s squared plus omega squared. But maybe it's shifted. So instead of s, you've got s plus a. Okay? So maybe it's a little bit like that. And maybe it's a little bit like a shifted cosine. So cosine is omega over s squared plus omega squared. But maybe the s is shifted a little bit like that. Right. So this is a possibility. And then you can use the first shift theorem. So what you have to do is write the s squared plus 6s plus 13 like that. And doing that is called completing the square. So that is our task now. Okay. So if you have a quadratic that cannot be factored, in this section what you do is complete the square. So write the thing on the left like the thing on the right. And the way you're going to do this is you're going to force the thing on the left to equal the thing on the right and basically see what happens. Okay, so it's written there, do what you want to do. There doesn't seem to be a whole lot of space there. Okay, but we'll do it down here. Okay, so let's start early. So you want to write s squared plus 8s plus 65 in the form s squared plus omega squared, but the s to be shifted to s plus a. So what we should do here is, now these are things we want to be equal. So we're going to multiply out the right hand side and compare. So if you carefully multiply out s plus a by s plus a, you get s squared plus 2as plus a squared, not s squared plus a squared, plus omega squared. And now we want to compare the left hand side and the right hand side. Now what have they got in common? They both have an s squared, so that's no problem. What about the coefficient of s on the left hand side? Well, it's 8. And on the right hand side, it's 2a. So I'm going to write that down. I want 2a to equal 8. And what about the other coefficient? That's the constant coefficient. That's 65. I want that to equal a squared plus omega squared. So I want 2a to equal 8, and I want a squared plus omega squared to equal 65. Right. So where are we? Now this is just an example. Okay, so we wrote this 2a, we want to equal 8, and we want a squared plus omega squared to equal 65. So this one is easy enough. We're just going to divide both sides by 2. We want a equal to 4. And then we're going to sub that in here. So we get 4 squared plus omega squared is equal to 65. Take away the 4 squared from both sides. We get omega squared is equal to 49. And then you do the square root of both sides. Now, the important algebra point, there are two numbers that square to give you 49, plus or minus root 49. You can make a choice here to pick one of them. Why would you pick the negative one? Just pick plus 7. Okay. So you have s squared plus 8s plus 65. That's here. If you force that to equal s plus a squared plus omega squared, you find that a has to be 4 and omega has to be 7. So that's called completing the square. It's obviously it's not factorizing because you're writing it not as a product but as a sum of two squares. If you can do it a bit faster in your head and you get it right, that's fine. But this is how I'll be doing it. Okay, so going back to our specific question, we've got 2s plus 1 over s squared. We've gone nowhere. We've just seen the technique, but like remember we tried to factorize, it didn't work. So we're still at the start. We want to write this like this. So let's do it. So let's force this to equal this. So we want s squared plus 6s plus 13 to be equal to s plus a squared plus omega squared. So the best thing is multiply this thing on the right out. So s plus a by s plus a. I mean, really, this I'll do it here, but I'm only going to this is at this stage you're in third year. S by s is s squared, s by a is a by s is as, plus a by a is a squared. And because these are numbers, sa and as are the same. So you have s squared plus 2as plus a squared, just in case you're wondering where this is actually coming from. So this is s squared plus 2as plus a squared plus omega squared. And now, and look, it's written down there, s plus a all squared is not s squared plus a squared, it's equal to that, which we showed you in light blue. So we're going to compare now. First thing to say is the s squares are grand. How about we look at the s's? So the coefficient of s on the left is 6 and on the right is 2a. So they're going to have to be equal. And then look at the constants. You have 13 here and that'll have to equal that. So you end up with 2a, the blue thing on the right, is equal to 6, the blue thing on the left. There's a good question here about what happens if you try and do this when it has real roots. Well, they won't be able to work, because if you look at s plus a all squared plus omega squared is strictly positive, it has no real roots. So if you have real roots, you can't write it like this. Well, you can do it with a minus omega squared, and if you do that, actually, that's how you find the minus b formula, by the way. Okay, where are we? So 6a is equal to 6. Sorry, 2a is equal to 6. Divide both sides by 2. A is equal to 3. That's good. And now the purple bits. A squared plus omega squared is equal to 13. A is 3, so it's 3 squared plus omega squared is equal to 13. So take away that 3 squared, that 9 from both sides. Omega squared is equal to 4. And divide both, take square root of both sides. Sorry, the baby's crying downstairs. It can be hard to concentrate. So very important, 2 roots, plus or minus, but we just choose one of them. We'll just choose 2. You can use the other one if you want. So we have found that s squared plus 6s plus 13 is equal to s plus a squared plus omega squared is 2 squared. Now, so we've done a little bit, so that's good, right? So we've started with this thing on the left, and we ended up with this thing on the right. Now, if you've done that, it's great. There's still a good bit to go, unfortunately. So we don't quite know what to do here, and the next bit is quite tricky. So what's very tempting is to do where you'd split up. There's probably, so this is the 2s, and this is the so maybe there's a bit in between here that we might just write out. So where's all this coming from? So you could do the 2s over s plus 3 squared plus 2 squared plus 1 over s plus 3 squared plus 2 squared. So I'm just saying that that's something that's tempting. It doesn't work, unfortunately, because so you can take the 2 out of the first thing, and that's what you're seeing in the first term here. But like both of the s's have to be shifted, and if you look at it, while the bottom s is shifted, there's no shifting on top. They both have to be shifted. So this didn't work. It just didn't work. Because look, it's written down below. If you want this to be shifted, both of the s's have to be shifted. Maybe we'll just write down a formula that is in the tables. The formula in the table says that the inverse Laplace transform of s over s squared plus omega squared is equal to cos omega t. And the important thing here is we're looking at the s over s squared plus omega squared. And if it's to be shifted, both the s's have to be shifted, like on the bottom, not like on the top. So that actually just doesn't work. So so how do we get away with it? Now there is a thing you can do. It says adding and taking away 3. Is it going to go through that way? Yeah, so I think there is another possibility, but it's longer. So what you could do is when you get to here, right, you keep this term on the right, but what you do is you put a plus 3 and a minus 3 and you'd split again. But it's a lot easier actually. The difficulty is the 2. It's just to get rid of the 2 at the start. So we're going to take out this common take out a 2 at the start. I'm not saying for a second this is easy. It's not. Okay, so we take out the 2 and we've got, so how does this work? Well, 2 by s gives you the 2s and 2 by a half gives you this. So you could say, okay, that is what it is. Now what you see, you want a plus 3 on top and a plus 3 on the bottom. So you add in a plus 3, but you minus 3 because otherwise you can't say that these things are equal. Now you've got, well, you've minus 3 plus a half, which gives you, so minus 3 plus a half is minus 5 over 2, and now you split. But notice that the 2, I'm not saying this is easy, notice that the 2 is actually multiplying both of them. So what I'm saying is here there's possibly a missing line. 2 s plus 3 over s plus 3 squared plus 2 squared minus 5 over 2 s plus 3 squared plus 2 squared, and now you can multiply in that 2 and you get the next line. So you get the 2 by, yeah, and then the other thing. Now this first term at this point is great. That's a shifted cosine. It's s over s squared plus 2 squared with the bits of shifting that we want to see. S shifted, S shifted. That's brilliant. Now the other term isn't quite there because if you look at it, and we'll write down the formula we're kind of aiming towards, is that the inverse Laplace transform of omega over s squared plus omega squared. So it's probably a good idea for you to print off that table, is sine omega t. And if you look at it, the omega should be 2, but we haven't got a 2 on top. So what you're going to do is there's a bit more going on here than even it's seen. So I'm just going to take just this bit. What you have to do is take out so I'm just going to write the bit in full stop. So the bit in the square bracket is equal to, so you take out the 5 over 2, okay, and then you have s plus 3 squared plus 2 squared, and what you want on top is a 2 because the omega here is 2. You want omega over s plus 3 squared plus omega squared. Now you multiply that by 2, you also have to divide it by 2. And so the bit in the orange, if I do the half by the 5 over 2, well, I'm going to keep the half there. So I end up with half by 5 over 2 by 2 over s plus 3 squared plus 2 squared. And look back, that's the thing inside the square orange. That has to be multiplied by 2. So the 2 by the half makes that half disappear. And you're left with the 5 over 2 and the rest of it. So no joke. Right. So this thing is ready to send back because look at the shifting. The first thing, just forget about the plus 3 for a moment. It's s over s squared plus 2 squared. And the other one, forget about the plus 3 for a moment. It's 2 over s squared plus 2 squared. So you've got a shifted, it's actually a truly shifted 2 cos 2t, the 2 on the front. And the other one is a shifted, well, minus 5 over 2 sine 2t. So we have something like this. So the crack then is, how do you bring back these things? This looks, this notation is very funny, but it works. So when you got the plus a, the shifting, so what I'm trying to say here is that if you have a shifted thing, you bring it back as normal, so that's the big F to the little ft, and then you multiply by this exponential shift. So are we going to, we're going to go for it here. So this, what's the name of this yoke? The name of this yoke is big F of s, so it'll go back to little f of t. So I'm looking, what am I looking at now? I'm looking at that. So that will go back to big F of, or little f of t. Fix the 2. So the next term, it's a shifted cos 2t. So what does the formula says? It says if you've got a shifted thing, you bring it back as normal. So that's the cos 2t. But because it's shifted from s to s plus 3, you multiply by e to the minus 3t. Okay. Then fix the minus 5 over 2, and we have a shifted sine 2t. So bring it back as normal, sine 2t. But because it's shifted s to s plus 3, we multiply it by an exponential shift, e to the minus 3t. No joke. And this is an underdamped harmonic oscillator. Absolutely no joke. Okay.